All right. So the rest of y'all can help us out here. The last several questions that you had were asking to write the equation of the tangent line. Now, it said write the equation of the tangent line in slope-intercept form, but you can't just write it in slope-intercept form right like that, okay? There's sort of an intermediary step, okay? But I know that y'all know how to find the slope of the tangent line, so we're going to find the equation of the tangent line, and they're always going to give you a point. You can find the derivative, then plug in the x-coordinate to find the slope, and then it becomes a problem like an Algebra 1 problem, where you would write an equation of a line that passes through a point and has a slope of -2. So somebody tell me in words, what would be the process, not doing here, what's the process that we would do on this?
You write out the equation of the slope and then you plug in the x and the y coordinate.
Okay, and so I'm going to say write the point slope formula. Y minus y1 equals m times x minus x1. And then you said plug in values, right? So we would plug in, so y minus, in this case, 5 equals -2, x minus 4. And step 3 would be manipulate to y equals mx plus b form. Manipulate to y equals mx plus b form. This is a very standard activity in calculus, namely finding the equation of the tangent line. Finding the slope of the tangent line is derivative, and this is finding the equation of that tangent line. Does anybody have a question on that? All pretty good?
Yeah.
We'll plan on grading that homework tomorrow when you walk in. Okay? Today we're going to talk about expanding your repertoire of what type of functions you can take the derivative of, okay? And we're going to expand that using something called the product rule and the quotient rule. Okay? So, let's go ahead and get started. We want to think about the derivative of two functions in isolation. Let's say I've got f of x equals x, and I've got g of x equals sine x. All right, good deal. Nick, what is the derivative of f of x? Mm-hmm. Yeah. No, not 0. So, you gonna try again? Somebody else want to help us out? Not 1x, nope. Just 1. Derivative of x is 1 because it's an x to the first, so we pop down the 1, then power down, and power down that 0, or that 1 turns into 0, x is 0 is 1. Okay, so see how your memory is. What is the derivative of sine? Cosine. Okay. That's all well and good. This is sort of like the remember. You're about to get a classic Mr. Goddard gotcha moment. We'll find out if it's there or not. Let's say we have h of x is equal to x plus sine x. We've talked about what's called the sum and difference rule of derivatives, and namely, if you have a function that is a sum or a difference of other functions and you want to find the derivative of it, then it's no big deal. You just take the derivative of the first part and take the derivative of the other part, second part, whatever. And that's 100% completely allowed. We saw that with our polynomials and things like that. Okay? So there's f, g, h. What's going to come next? I. See, I is normally kind of imaginary. J, same, K, L. Let's go with P, I guess. So P of x now is going to be x times sine x. This is a product. And you might think that the derivative would just be 1 times cosine x, right? That's what you might think that. So 1 times cosine x, where similar to the sum rule, it's like the derivative of x is 1 and the derivative of sine x is cosine x, okay? But it is not. That's the hammer. Okay? If you have two functions multiplied together, it is not just the product, the derivative is not the product of the first, or sorry, the derivative of the first and the derivative of the second. That is not what it is. And I wonder if there's a way that I could show that to you. Maybe local linearization. What does the graph of x sine x look like? You all have your calculators, right? Let's go ahead and graph x sine x. No calculator, calculator. Do I grab a calculator? Do I have to go as part of the procedures here? That one doesn't have battery. This is calculus, so make sure you're in radian mode. Let's zoom out to see what kind of
Looks like the M from McDonald's.
What happens if you zoom out?
If you zoom out. Do you zoom out?
X sine x. Grab it. Make sure you're in radian mode. So if you zoom out again. Not sure what's going on with that one. Oh.
Zoomed out too much. Well, looks like a butterfly.
And that's a problem. This is a single zoom out.
Yeah, I already done that one.
Okay. Something like that? Yep, use zoom out button once, okay. Yeah. So, for those of you that remember from trig, what is this number that's, when you have sine function, which we all know goes up, down, back, center, what does that number out in front do? If it was 5 sine x, what would that do? Yeah, it changes the amplitude, okay? So we have, you know, when we're in the 1, 2, 3 area, then our amplitude is 1, 2, 3. When we're in the 10, 20, 30, 40, the amplitude is 10, 20, 30, 40, 50. And so that amplitude gets bigger and bigger. So the sine function keeps going higher and lower and higher and lower. Now, just to prove my point, if the derivative was just 1 plus cosine x, then that slope would get really, well, I can put it this way. We know what cosine looks like, right? And we know that the cosine is the derivative of sine. And there's no way that the cosine is also the derivative of this crazy thing, which is getting higher and lower and steeper and shallower. Does that make sense? I don't know if I can say that again. We know that cosine is the derivative of sine, so there's no way that the cosine is also the derivative of x, sine x. Okay, there you go. There's my point. So what we got to do is we need to figure out what is the derivative of one function times another function. If my little poorly executed argument doesn't make sense, just take my word for it. It's not. You can't just take the derivative of the first part and the derivative of the second part. You've got to do something different. And this is going to require about a page of paper for us to figure it out. All right, so here we go. We want to take the derivative of f of x times g of x. And we want to be able to do this for any problem, anytime, anywhere, not just x and sine x. So I'm going to make this extremely generic. And if you remember, the way that we take the derivative is the limit as delta x approaches 0 of all of this thing right here, so f of x plus delta x, g of x plus delta x, minus f of x, g of x, all over delta x. Are you all in agreement? Next step. This will be a big one. So I'm going to write this part right here again. So the limit as delta x approaches 0 of f of x plus delta x, g of x plus delta x. And then I'm going to do what in math circles we call an unmotivated step. I'm going to subtract something from here and add that same something to it. So I'm going to subtract 5 and add 5. Okay? For reasons which become obvious in a minute. But y'all know if you subtract 5 and then add 5, where does that get you?
Same place.
Same place you started from. Yes, this is like adding 0. So I'm going to say minus, somebody had a lot of time on their hands to figure this one out, I'm telling you. F of x plus delta x times g of x plus f of x plus delta x times g of x. Blue indicates the new, minus f of x, g of x, all over delta x. Next, I'm going to notice that this term and this term both have an f of x plus delta x. So what I'm going to do is I'm going to factor that out. So I'm going to say limit, I'm going to put a little bracket here for the whole thing. So f of x plus delta x times whatever's left over in this part here, g of x plus delta x, minus whatever's left in this term, g of x. See if that makes sense to you. Cody, do you see those two terms that we factored out? F of x plus delta x. We just pulled it out here, and then this is left over and that's left over. Does that make sense? Okay. Look at these terms over here. What do they have in common?
G of x.
G of x. So I'm going to say plus, and I'll factor out a g of x right there. And then we have f of x plus delta x minus f of x. All right? And then I'm going to split this up into two parts. I'm going to say this, I don't know if you remember doing this, but actually you probably never did. Whenever you have fractions that both have the same denominator, you can just like kind of combine them. Like if you had like 3 over 4 plus 5 over 4, you could do that to be 3 plus 5 over 4, right? If they have the same denominator. Okay. We're just going to go in the opposite direction here. We're going to split up the fraction. We have this plus this all over delta x. And what I'm going to do now is I'm going to write this as a fraction. So f of x plus delta x times g of x plus delta x minus g of x all over delta x. And then over here I'm going to write plus, and I'm going to write all this stuff over delta x. So g of x times f of x plus delta x minus f of x all over delta x. And I'm gonna start doing a couple things at the same time. I've got the limit of this plus this. What I can actually do is I can write the limit statement here. Limit as delta x approaches 0, and the limit as delta x approaches 0. Any questions so far? Okay. Here's another fraction fun fact here. So sometimes you had like a whole number, like 5, and you would multiply that by like, I don't know, 7/8. When you multiplied that, y'all know that you would just multiply, you didn't have to get a common denominator, you would do 5 times 7/8, right? Pretty straightforward. Okay, we're gonna go the opposite direction now. We have this times this over this. So now we're just gonna kind of split it up. So we're gonna write it as f of x plus delta x times g of x plus delta x minus g of x all over delta x. So I'm sort of just peeling this part off here. And I'm going to do the same thing over here. I'm going to write g of x times f of x plus delta x minus f of x all over delta x. And I guess I better write the limit delta x approaches 0 of this thing. Limit delta x approaches 0 of that thing. And a property of limits is that if you have the limit of blah and times blee, you can actually write the limit of blah, so take the limit of this function right here, and then times the limit of blee. Yeah, I'll just write it down there. So, actually, the step after this is really awesome. So I'm going to carry that over here. So I'll write the limit as delta x approaches 0 of f of x plus delta x times the limit as delta x approaches 0 of g of x plus delta x minus f of x all over delta x plus the limit of the first thing times the limit of that second thing there. Limit is delta x approaches 0, g of x times limit is delta x approaches 0 of f of x plus delta x minus f of x all over delta x. So at this point, you are beginning to reevaluate whether or not you should have taken this class. Because you think, if this is what we're doing in class, is this what we do in homework? And for anyone that took my pre-calc class, you know the answer is no. Right? What we do in class is we show you how to get there. We show you the stuff that you can't do on your own. Right? We show you the proofs, the derivations, how to, the reason behind the reason. For homework, you just practice it, all right? Where we're going with all this is an awesome formula that you're going to be able to use in about 20 seconds. Not 20 seconds from now, but this is a 15-minute proof. Okay? So, time to shorten things up a little bit. Let's look at this part right here. Limit of f of x plus delta x as delta x approaches 0. Can we do direct substitution on this thing right here?
Yeah.
Jeremy says yes. I'll hear some other yeses. If we just do direct substitution, then that delta x turns to 0, right? So what does this thing turn into? Just f of x. Now a harder question. What the heck is this? The limit of g of x plus delta x minus g of x all over delta x as delta x approaches 0. Can we do direct substitution on that?
No.
Because?
0.
Right. But that looks really familiar.
We can do that other one, that function. I forget the name.
Multiply by something, and then we're not going to use any algebraic techniques here. We're just going to do a single substitution. If anyone can recognize this formula, does anybody recognize it?
Oh,
We don't normally see with the G. What's that? Yeah, that's the derivative formula. Good job. Yes. This is the derivative, but I've replaced f with g. Look, limit g of x plus delta x minus g of x over delta x. Right. So this right here is g prime.
Wow.
Right? That's what it is. That's kind of the motivation behind this whole thing. Plus what about here? Can we, limit of g of x is delta x approaches 0. Can we do direct substitution there?
no, there's no delta.
Actually, yes, because there is no delta x.
Oh.
There's nothing to there's nowhere to plug it in. So it's literally,
just 0.
no, it's not just 0, it's just g of x. What I'm saying is, g of x is always the same as delta x approaches 0 because g of x doesn't depend on delta x. It's just g of x. Now, someone other than Chloe, does anyone recognize this thing over here? What is that? Derivative of f of x. So I shall write f prime right there. And hey, what do you know? That's our answer here. This is the product rule. F of x times g prime of x plus g of x times f prime of x. Also known as, so think of it like this. So f of x is our first function. G of x is our second function. So the derivative with respect to x of f of x times g of x is the first times the derivative of the second plus the second, and by second I mean the second function, times the derivative of the first. F times g prime of x plus g times f prime of x. Class, repeat after me. The first times the derivative of the second
Times the derivative of the second.
plus the second
Plus the second.
times the derivative of the first.
Times the derivative of the first.
Alright, so a little faster now. The first times the derivative of the second
The first times the derivative of the second.
plus the second times the derivative of the first.
Plus the second times the derivative of the first.
Good, good. So now we can apply it. Anybody still need that? Okay. So if I have f of x is equal to x times sine x, x is my first function, sine x is my second function. So f prime is the first, so that's just x, times
The derivative.
derivative of the second. So derivative of sine is cosine. Plus the second
Fine.
sine x times the derivative of the first. So the derivative of x times sine x is x cosine x plus sine x. That is the product rule. Let's do another one. So g of x equals cosine x times 3x squared. So it's a product, so product rule is the first.
Times the second.
Yeah, okay, so I would just, so set cosine x times the derivative of the second. What is, anyone? The derivative of the second is 6x plus
The derivative.
No, plus the second.
Oh, yeah.
So that's going to be 3x squared times,
The derivative of the first.
which is, what's your cosine, Rosa?
Negative sign.
Negative sign. Normally when it comes to trig functions and things like that, we put the numbers and constants and variables first. So we would say 6x cosine x, and that minus, we'll put up here, so minus 3x squared sine x. All right, are you happy? First times the derivative of the second plus the second times the derivative of the first. Let me give you another one here. So h of x, this is one y'all gonna work as a table, equals square root of x times sine x. Ready, go. Alright. We don't like that kind around here, right? We don't serve radicals, we just rewrite that as 1/2, right? So, somebody call out to me, what do y'all have for the derivative? First, call it out.
X 1/2. Cosine x.
Somebody else?
Plus sine. Times 1/2 x to the.
There, 1/2. Sounds good to me. Alright. Things are really slowing down here. A lot slower than I'd like, but that's okay. So tomorrow we are going to take a memorization quiz, and we're also going to talk about the quotient rule. We need to grade our previous memorization quiz. Alright? So today you talked about the product rule. You don't have any homework. If you haven't taken notes on 3-4, you better do that, because I haven't checked it yet, but that's some good stuff. And grab a red pen. You're going to grade this memorization quiz yourself. Emily, can you turn off that recording device?